Hello, my lovelies. Now we are going to examine if there's more than one thing that we want to know the probability of. So 2 or more events together. So we have first this idea of independent versus dependent. So dependent, depend is the root here. 2 events are dependent if one depends on the other. So if the results of the first event will impact or change the probability of the second event. And then independent is the opposite. The results of the first will not impact or change. In fact, it is so that I'm going to be real lazy. There we go. Okay. So we got those defined. So if 2 events are independent, then we just figure out the probability separate and then do whatever we're going to do with them. When they're dependent, we have to be a little more careful depending on what kind of question is being asked. So last set of videos, I hinted at that we were going to come back to the and the or concepts. This is where they are. So and probabilities is when you want to know about 2 things occurring. So you look at whatever the first event is and see if doing that first thing is going to have an impact on the second thing. Now, some problems, there's no obvious first or second. Like here, we're tossing 2 dice. They're 2 separate dice. It doesn't matter what I get on one for the other. So that's pretty common for simultaneous events. It's for events where you're doing, I do a thing, then I do a second thing. What happens on the first can impact the second, like what you do. Okay, so I'm going to toss 2 dice. I want to know the probability that they're both going to get a 1. So how you do this is we're going to figure out the probability for one die getting a 1, and we're going to figure out the probability for the other die getting a 1, and then we multiply them together. So and probabilities. If they are independent. I mean, you multiply even if they're dependent, but you have to be more careful then. So here, this is the probability of getting a 1. And then I've just got that one, the probability of getting a 1. Now it should have said this is a 6-sided die. Like I said before, though, just assume it is. Or if you're not sure, ask. It's a fair question if you're a geeky gamer like I am. So 1 out of 6 times 1 out of 6. And those just look naked without parentheses to me. I'm sorry. There we go. And that gives us the lovely result. Multiply the tops, multiply the bottoms. See, this is why you guys were doing fractions. Or just crunch it on the calculator for me. But 1 out of 36. When we talk about probabilities, a lot of times we prefer the fractions, and that's because the decimals of these are repeating. And we end up with a lot of repeating decimals. So that's why we tend to stick with the fractions here. But realistically, I don't know what 1/36 is like as a decimal. I don't know how big it is. I mean, I know it's small, but let's see. Parentheses are very important. Now, some calculators, if you just write 2 things in parentheses next to each other, it'll multiply. The computer is a very literal creature, so I prefer to give it that multiply in between so it knows. So 0.0278. All right, that's pretty tiny. Almost 3/100ths. Now here we go. Find the probability that a 100-year flood will strike a city in 2 consecutive years. Assume a flood one year does not affect the likelihood of a flood the following year. Let me just cross out flood and write blizzard. Okay, so when we use the phrase 100-year flood, that phrase means a flood like this only happens once every 100 years. So that's unpacking that little colloquial English phrase. So, and it tells us flood one year does not affect the likelihood of a flood the following year. So we just need the probability of one of these floods happening. And then we're going to multiply it again because we assume it's the same probability. And it's once every 100. So 1 per 100, 1 over 100. So we have 1 100th times 1 100th. And that gives us 1 hand tremor. 10,000th. Which that is, so that would be 100th, 2 places. Like that's tenths, then 100th, 1,000th, 10,000th. Teeny tiny decimal. Still, I don't like that because that's having to make an assumption about what an English phrase means, which is bad enough when you speak English, but if English wasn't your first language, it's 20 times worse, if not more. Okay. So now we have a box of candy. It only has 5 chocolate pieces and 5 caramel pieces. This is a small box. Oh well. What is the probability that you will randomly choose 2 chocolate pieces from the box in a row? Now, what they did not state here, but which, should be implicitly obvious, it's not. They really should have said it. When I pick the first piece, I'm going to eat it. So I'm not going to put it back in the box. So after I do the first one, then the second one, the numbers in the box have changed. Once I eat the first one, now there's only 9 candy pieces left. So this is what dependent events are. What happens on the first one is going to impact the probability on the second one. Okay. So when we're going to do dependent events, what we do is we do the probability of A, the first one, and again, we still multiply, and then we have the probability of B given A. Now, sometimes they will write B given A. Put a little more space here. As the probability of B, and then they'll use this little pipe symbol, which is on the right side of your keyboard above the enter. It's the shift for the backwards divide. You get a little vertical line. It's called a pipe for really strange reasons, actually. The history on it is kind of silly because it's not a pipe. So it's called a pipe because it's not a pipe, and it's based on a painting by Magritte that he painted a pipe and said, this is not a pipe because it's not a pipe, it's a painting. It's very silly. Computer people have weird senses of humor. Okay. So my first chocolate. I got 5 and 5, so I got 10 pieces. 5 of them are chocolate, so I got a 5 out of 10 probability of getting chocolate on my first eat. So 5 out of 10. That is the probability of getting a chocolate on the first pull. Now, when it says the probability of B given A, that means we assume A happened. Now, what is B based on A happening? So here, let me doodle a little bit. So 1, 2, 3, 4, 5. Sure, those are caramels. 1, 2, 3, 4, 5. There are chocolates. Yeah, just go with me. In the box. This works because the numbers are small. If the numbers were ridiculously big, I'd say shove small numbers in there, figure out what you do, and then put the big numbers back in. That's one of my like go-to problem solving things. If I don't know what the operation is supposed to be, that's how I figure it out. All right, so the probability of A was, I'm going to eat one of those guys. There are 5 of them, and there are 10 total. So 5 out of 10. But, nom nom. Why not? So it is gone. Now, how many candies do we have? So the probability of B given A happened. Now there are only 9 candies. And I'm assuming that that candy I pulled was a chocolate because I want to know the probability of choosing 2 chocolate pieces in a row. So now there's only 4 chocolate pieces left. So the top here is going to be 4 for 4 out of 9. Like I said, though, they really should have said, because here it says choosing. And for some people, like, sure, I can choose the candy without eating it. Like, it's not a good verb choice. So if you're ever not sure on something, shoot me an email. If something weird happens on Alex in regard to something like this, shoot me an email. I can go in and argue with it. All right, now we still multiply. All right. So 5 times 4 is 20. 10 times 9 is 90, which both are divisible by 10, so we get 2/9. So there is a 2 out of 9 probability that I will pull 2 chocolate pieces from the box for my first 2 pulls. That question is really written badly. It shouldn't even say in a row because that, anyway, like it should say in the first 2 pulls. Okay. All right, now we have bingo. B-I-N-G-O. It's a shame my daughter's not here. All right. The game bingo involves drawing labeled buttons from a bin at random without replacement. Sure, yeah, buttons. Balls, please. Well, no. I guess they were buttons, huh? I've only gone bingo once. So there are a total of 75 buttons, 15 for each letter in bingo. What's the probability? So B has 15, I has 15, N has 15, G has 15, O has 15. And technically the numbers go from 1 to 75. The first 15 are the B's, the second 15 are the I's, and so on. But they're just focusing on the letters here. So what's the probability of drawing 2 B buttons in the first 2 sections? Now, here is the happy phrase that we should have seen earlier and did not. Without replacement. Without replacement means I'm not putting them back in after I draw them. So that way I don't draw the same thing twice. So when you see without replacement, I want your brain to think, oh, this is probably dependent. Because once you're not putting something back in, the probability of the whole bag changes, or the whole bin, or whatever you want to call the thing. I usually think of a bag of marbles. All right, so 2 B buttons. So the first B button, there are 15 out of the 75. Now my second B button, I'm assuming that I drew a B on the first one. So now instead of 15, there's 14. And now instead of 75 total, there's 74 total. Now, I'm sure those will do some happy number crunching dance. So it's 1/5 times 14/74, which would be what, 7/37. So it looks like you get 7 over whatever 5 times 37 is. 185. Math. This is why you guys have calculators. Even I'm kind of like, I'm hesitant about that. Okay. So that's assuming my first two are B's. So that from the 15 to the 14. Now, if it was I draw a B and then I draw something else, my top number would still be 15 because that something else has 15 in the bin still. All right, then we have what's the probability of drawing 3 N buttons in the first 3 selections? Well, we just figured out drawing 2 of the same thing for 2 selections, so we just got to tack on one more. I'm not crunching this one. It's going to be gross. So we have 15 over 75. There's our first N coming out. So now there are only 14 and there are only 74. And now our third one coming out. So 2 of the 15 are gone, leaving us with 13. 2 of the total are gone, leaving us with 73. So we multiply the tops, multiply the bottoms, and get a very disgusting result. Whatever 7 over 185 is times 13 over 73. Ugly numbers. Honestly, these fractions are so ugly, I think they would actually ask for the decimal instead. And because probabilities are always between 0 and 1, we usually go with 3 decimal places. It will tell you. Alex is really good at remembering to tell you rounding directions. But let's go ahead and crunch these and see what the ugly numbers actually are. So I'll go ahead and start from the beginning. 15 over 75. And this is one of the reasons why I write my parentheses when I'm doing math, is for when I'm going to type. And then 14 over 74 equals ugly mess. Okay, so that is 0.0378. You can think about probabilities as percentages. So we would say about 3.7, 3.8% of the time, you could pull 2 B's on your first pull and second pull. Now we're going to take that result and multiply by even uglier. 15 over 75 times 14 over 74 times 13 over 73. Some calculators will do it fine without the parentheses, but I grew up in an age when calculators weren't always programmed correctly and they mattered. So now 0.0067. So that is 2/3 of 1%. A fractional percent. Less than 1 out of 100 times will you get the first 3 being the same letter. Because if I change that to I's, it'd still be the same probabilities. All right, so that's the idea of dependent. Your numbers change from the first to the second and whatever events afterwards. Now I'm going to cut the video and then come back.